Thank you. Thank you very much for coming. Yeah, my name is Alex from Hamamatsu, Photonics, and I want to talk about our lasers, and you already see some keywords like sustainable rapid processing and high volume production in the subtitle, and I hope that after the talk it gets clear to you why we think these are the big arguments for the laser itself and print electronics. First of all, some facts about Hamamatsu. Japanese company established in the 50s. We are about 5.8K employees. Most of them are working in Hamamatsu City, where our production is based in Japan, so 1.5 hours in the south from Tokyo by Shinkansen fast train. We have more than 15,000 products, all in the photonics field. I want to talk today only about the lasers, so we cannot cover all today, but this is one of our light source, and the 3 Nobel Prizes which are enabled by Hamamatsu technology, which, by the way, it was the Kamiokande project for neutrino detection, characterization, and one of them as well was detecting the Higgs boson, so that's a very nice thing to be proud of. Okay, so I want to talk now a bit about my passion about the lasers, exactly which are manufactured and established and basically developed by Hamamatsu Photonics. These lasers are diode lasers, semiconductor lasers, and we have 2 versions of it. Basically, we are starting with the fiber-coupled version. You already see it, this green fiber. The laser irradiation is generated in this module rack. It's a continuous wave operation, so it's not pulsed. So we like to have the thermal energy on the irradiation spot. That's why we are using the continuous wave operation here. The emission wavelength is 940, so it's a near-infrared laser. And the maximum output power of this is 360 watt. We have different versions which has slower or smaller power. Depending on the application, depending on the customer's requirements. This unit basically is for placing it somewhere else. The compact unit with the fiber supply and the power supply inside, and basically it's very easy to use, easy to integrate, and that's what we also see in the print electronics field. If the power is not enough, sometimes you need more of it. Sometimes you need 1 kilowatts or even more. We have direct diode lasers, which are not fiber coupled. Also, the power supply is somewhere else. It's usually in a rack, but this is the laser head itself. It's, again, a continuous wave laser, emission wavelength 940, and maximum output power is here 5 kilowatts. For the print electronics field, that's way too much, but of course, we have also smaller units which are basically also more compact and easy to integrate for roll-to-roll, which is basically also one of our targets. Here you can see some of the classic laser applications which are enabled by diode lasers. One of them is, for instance, plastic welding and soldering, very classical ones. Today I want to set a focus on the print electronics, of course, and one of the applications which is of course really interesting is the sintering, the post-processing, the thermal post-processing of the print electronics itself, which is a very important step to create the conductivity, curing, and of course the adhesion strengths. Another comment, we distinguish between curing and sintering. For us is curing removing the solvent, and the sintering part is creating the conductivity, so melting the particles together, and that's basically difficult to achieve with the laser itself, so that's why we like to use pre-drying in advance, but creating the conductivity, that's basically the main job of the laser, putting the thermal energy on the traces in a very short term on a very high temperature and creating a good conductivity including adhesion strengths. So on this picture, you see 2 different irradiation approaches. On the right side, you see the spot. So we are basically able to irradiate the laser, which basically comes